All right, let's go over a quick review of oxidation and reduction and what we learned so far. This table is found in the reference table. It's table J. We'll come back to that in just a second. But first, I just want to talk about the first thing that we mentioned was these electrochemical cells. So electrochemical cells utilize electrical energy in different ways. There's two types of electrochemical cells. The one that we focused on first was voltaic cells, and then the other one is electrolytic cells. We haven't talked about those yet, but we'll get there. Voltaic cells take chemical energy and they convert it into electrical energy. Now, in a voltaic cell, the major component that you'll need are two electrodes. All right, so the first electrode would be an anode, and the other electrode that you'll need is a cathode. Now, these electrodes allow electrons to flow through. Remember, these voltaic cells are pretty much just batteries, and the electrodes allow electricity to flow from one electrode to the other, typically from the anode to the cathode. Now, an anode is the electrode that gives electrons, and then the cathode receives the electrons. So electrons come out of the anode and are transferred to the cathode. Now, this process of giving electrons, this is also known as oxidation. So when we refer to oxidation, that just means losing electrons. And then this process of receiving electrons, this is called reduction. So when we say reduction, that's just what we're referring to. We're talking about receiving electrons. Next, we talked about the chemical reactions that happen at the anode and the cathode. So at an anode, we're going to be looking at things that give electrons. So for example, a pretty common anode would be something like lithium. Now, when lithium gives an electron, because it's in group 1, it will end up being lithium with a positive 1 charge. And then since it's giving 1 electron, we write plus 1 electron on the product side. Now, a pretty common cathode would be something like copper. And the cathode will start off usually with a positive charge. And since copper here has a plus 2 charge, it needs to gain 2 electrons. So the electrons are written on the reactant side because they're being added to the cathode. And then our product would just be plain old copper. Now, next we talked about combining. So these reactions here, these are known as half reactions because it's only half of the reaction that's happening inside of the battery. But we want to look at the whole thing. So we want to combine these into one reaction. But the only thing we have to do first is make sure that our anode and our cathode are giving and receiving the same amount of electrons. Right, so in order to make sure our anode and cathode are giving and receiving the same number of electrons, we would, in this specific example, we want 2 lithium, right? Because then if we have 2 lithium, they'll give 2 electrons. And then my copper will still be taking 2 electrons. And then our electrons will pretty much just cancel out. And so now we can really just combine these into one chemical reaction called an oxidation-reduction reaction, otherwise known as redox. So we'll write it as 2 lithium plus Cu2 plus, and this goes to 2 lithium plus copper. All right, so that would be our balanced redox reaction. All right, one of the last things that we talked about was just being able to identify when you're looking at a redox reaction. So if we have, for example, FeCl3 plus SnCl2, and these go to FeCl2 plus SnCl4. So if we have, this is not really balanced, by the way, but if we're looking at this reaction, the first thing you want to do is assign oxidation numbers. So we want to be able to tell, is this chemical reaction an oxidation reduction reaction or is it not? So chlorine will pretty much always be -1, and there's 3 of them, so I'll write -1 3 times above it. And the oxidation numbers have to add up to 0, so that means my iron will be a +3. So chlorine over here will be -1, -1 for the same reason, and so my Sn, or tin, will be +2. Fe over here will be +3, chlorine -1, -1. These will be -4, so 4 little -1s up there, and then my Sn will be +4. Now we just have to look to see, is something losing electrons and is something gaining electrons? So we'll look at iron. So iron went from a +3 charge to a +2 charge, and so that means it gained electrons, and that is reduction. And then my Sn went from +2 to +4, and so that just means that it lost electrons, and that is oxidized. And so you can look at this reaction and say, hey, something was oxidized, something was reduced, and so yes, this is a redox reaction. All right, and then the last thing was, you want to be able to look at a reaction, a redox reaction, and say, is this spontaneous or is it not? So spontaneous just means that it will happen kind of on its own without any outside forces required. So let's look at this reaction. So we have zinc and H2SO4. And this goes to ZnSO4 plus H2. Okay, so we'll assign our oxidation numbers. Remember, elements not bonded to anything else get an oxidation number of 0. SO4 is a polyatomic ion that gets a -2. And then H, we get +1, +1. Zinc will be +2. All right, so zinc is going from a 0 to a +2. So this lost electrons. That's oxidation. Hydrogen went from a +1 charge to a 0 charge. So that gained electrons. That's reduced. Now, we have to look at table J to see if zinc can give its electrons to hydrogen. So we want to ask the question, is zinc more active than hydrogen? All right, so we'll look back at table J. So we can see zinc is right here, hydrogen is over here. And so because zinc is more active than hydrogen, so the metals higher up are more active, that means that zinc can give electrons to hydrogen, but hydrogen cannot give electrons, back to zinc. So let's go back to this. So yeah, zinc will give its electrons to hydrogen spontaneously, and so we would say, yes, this is a spontaneous reaction.